That depends. Right now, okay, this is the one before. This is the one before last week of the semester. So we have lectures next week, Tuesday, Thursday. The reason why I told I'm considering the option of having an extra lecture is because what we're going to do next week is mainly the Higgs mechanism, and I don't want to end up before we finish the Higgs mechanism. I think we should be able to finish it. Yeah, I think it's very easy for me to finish it. The question is how much you're going to understand. I know it, especially that you know it again. The whole point is to make sure that you understand something, right? So that's why I'm going fast, but hopefully not too fast. If I'm going too fast, you tell me. Okay, that's the idea. And what we do now is actually sort of introduction to the Higgs mechanism. We're going to need that next week. So yeah, so if we don't finish discussing Higgs mechanism by next week, then instead of rushing or stopping in the middle, the more logical step would be to add up another lecture. But I'm not sure if we're going to need, actually likely we will not need an extra lecture. Cover the basics. As you can see from this, I mean, this is really an introductory course. You can see that there is plenty of things which we barely touch upon in this course, and there is a whole subject that I'm basically skipping. That's what we can do. The thing I'm not skipping is this thing which is called gauge theories. Theories, QED and QCD. Nearly finished writing your homework for today. I actually finished writing the homework, but I didn't finish solving it. Before I solve it, I don't put it. I have to solve it first to make sure that there's no mistake in there. So hopefully it will be today, maximum tomorrow, to get the new problem set. What did we do? So a quick recap. I spoke about the Lagrangian, which is something which you're all supposed to know. We spoke about Lagrangians in classical mechanics, which is something which you're supposed to know. And then I said Lagrangians in QFT. Questions? Lagrangians in QFT, we said instead of L of Qi and Qi dot, we're going to Lagrangian density, L, which is a function of the fields and their derivative. Then of course L is just integral dqx of the Lagrangian density. It's technically it's Lagrangian density, but everybody calls it a Lagrangian. It's just a Lagrangian, and S, the action, is integral d4x of the Lagrangian density, which makes sense. And then Euler-Lagrange equation of motion is that. And I gave a few examples, both classically, and then in quantum field theory, we wrote down the Lagrangian of relativistic scalar field. Right. S, which is 1/2 d mu phi minus 1/2 m squared phi squared And then the Euler-Lagrange equation of motion is simply the Klein-Gordon equation. Then for the relativistic spin half field, note that I call it field, right? It's not quantum field theory. A particle is really field. And then, of course, we have the Dirac-Lagrangian. And the Euler-Lagrange equation is, of course, the Dirac equation. And for relativistic vector field, it's 1/4 F mu nu minus J nu, or mu, A mu, and the result is Maxwell's equation. Have more to practice that in your homework. Then we spoke about Netter's theorem. We said that every continuous symmetry of the Lagrangian gives rise to a conserved current. And the last thing we did was looking at a specific example. Well, I have two examples. One which is the classical example, right, of a body influenced by gravitational potential of a massive body. This is something which I believe you've seen. And the thing that I believe you have not seen is the U1 symmetry. So global U1 symmetry of the Dirac-Lagrangian psi x goes to psi prime of x, which is E I Q chi psi of x, which is U chi psi. Global means that it is independent on the coordinates, so it's everywhere the same. And we saw that Dirac-Lagrangian is symmetric under this transformation. Just a second. We saw that the Dirac-Lagrangian is symmetric under this transformation. And that gives rise to a conserved current, J mu, which is Qi psi bar gamma mu psi. This is the conserved current. Which really means d mu J mu is equal to 0. Yes?
What's the difference between Q and chi? Because both of them are just numbers.
In the global, it doesn't mean they're not really. There's no difference. In the local one, Q is going to be still a number, and chi is going to depend on the space. Okay, and you have to complete that at home to show that this really represents the total charge, thereby completing the proof. Questions? No? So at the end of the day, it does make sense, but you know, if it's the first time you're seeing the thing, like, there's no reason to believe you already saw that. It can be a bit confusing. Yeah. This is a global phase, basically. I'm taking the field psi, and I add it. I put some global phase in it. And I'm saying that the Lagrangian is invariant. It's not changed. No, that's the meaning of a global. Global means that chi is the same everywhere. If chi was a function of x, there would be a local. It would not be global. Yeah? More? No.
Excuse me? Why you decide that Q is the charge?
What?
Why you decide that the Q that is in the global transformation is a charge?
Q here is just a number that
It's just a number, yeah?
Yeah, but it will appear in the current, and then when you do your homework, you'll see that this is actually the total charge.
Because it's a constant, you can define the current without Q.
In principle, yes. And, but then it will be difficult to find what is the physical meaning of that. Okay. Now, I mentioned these Lagrangians, they're nice. They look nice, you know, they're very compact. They represent particles, but what we don't have here? Interactions. So, you know, I can put this term, these Lagrangians, and physically that will mean that I assume that there are particles that exist, but it's boring. The particles are not doing anything. Now, what we want is to add interaction. And for that, we need to put some additional term in the Lagrangians. And now comes the real trick, right? That I'm going to show you. What we did with that was a global symmetry. Now there is a way of taking a local symmetry, right, and making the, in order to make the Lagrangian invariant under a local symmetry, we'll have to add term to the Lagrangian. Okay? Otherwise, if I just take that, it's not going to be invariant for any local symmetry. But this term, what are they? These will be the interactions. So that means there is something extremely deep here. That means that the interpretation, this interpretation according to Hermann Weyl, right, he first proposed that the interactions have really a geometrical interpretation, in a way. Right? Because I'm asking the Lagrangian to be invariant locally under various transformations, and from that gives rise to new terms which really are interactions. So every interaction we see means that there is some hidden symmetry somewhere there. That's a very deep idea that affects physics, particularly particle physics, but not only. Right? That all the interactions we have in nature really originate from some hidden symmetries. Right? Take a second to digest what I just said. Okay? It's a beautiful idea. Now let's see how it works. Local gauge invariance. So, the questions to be solved. how do we describe interaction? And related to that, are all interactions allowed, or there is a certain principle that forbids some of the interactions and enables others? What interactions are allowed and what not? What interactions are allowed and why? And why is meaning, is there anything deeper here? So the idea goes back to 1929, so that's nearly 100 years ago. In 1929, that's a mathematician named Hermann Weyl. For those who took the course in general relativity, it's the same Hermann Weyl. Won't surprise you. Proposed the idea of the gauge principle. Well, gauge principle. Black horses with principles. Principle of invariance under gauge transformation. Basically, this is a method of how to get to interactions. We take any global symmetry, like the one we just saw, and we localize it, right? And we see what terms are added to the Lagrangian. And we add these terms to the Lagrangian, and these terms will represent interactions. Okay? I have an example which I'm not so sure is that great. I'll give you the example, and hopefully it will not confuse you. Example. Let's say the 1D example. So let's say we have a function f of x. Function f of x. Right. In any nearby point, right, we can write down f of x plus dx is f of x plus df dxf dx. Right? Now, what is gauge, by the way? Think about gauge invariance. I'm sure you've seen the word gauge. What is gauge? Pure. What does it mean? Right? It's scaling, right? It's changing the scale. Having selecting a gauge means selecting a scale, different scale, right? So scale, gauge, means scale, means units of measurements. Unit of measure. So what I said, let's say in addition to changing the function, let's change the space itself. Okay, so you can stretch a space. So that's Weyl's idea is stretch space. Right? Let's say by a factor of 1 plus s dx. Now we're starting to stretch the space. So that means that the value of the function f x plus dx is now f of x plus dxf dx, which is evaluated in the new location, which is 1 plus s dx. So this is f of x plus dxf of x, right, plus f of xs dx plus O of dx squared, which we don't care. So the increment in the function f when we go from x to x plus dx is now that, right? This is the increment in f from x to x plus dx. Okay? Now, by selecting how we gauge the space, how we stretch or you know, stretch or compress the space, we can make this equal to 1. So we can make this function invariant, basically, by selecting how the space is stretched, we can modify the value of f x plus dx. And what does it mean, stretching space? Essentially, that would correspond to some interaction that we have there. So really, it's a geometrical interpretation of an interaction. We have an interaction, and we give it some geometrical interpretation of that. It stretches space. So there is something quite deep in here. In other words, essentially all the standard model interactions can be derived from this gauge principle. All standard model interactions can be derived from the gauge principle. Meaning that it's as important to physics as Hamilton's principle. I would say that this association that Hermann Weyl tried to say, the geometrical interpretation is not always working. This is always true. This is not always working. So in that sense, Hermann Weyl was a little bit too optimistic. Okay. Does the basic idea is clear to you? Let's apply it. So last week, was Tuesday, right? We looked at the global symmetry, the global phase symmetry. Now make it a local symmetry. So local symmetry This is also what we call gauge symmetry. Involves local transformations, obviously. Which is a transformation that does depend on space and time, locally. So, in particular, let's look at the local phase transformation. U1, local. So psi of x, we go to psi prime of x, which is E I Q chi of x. That's the difference, right? You're asking about psi of x. Which is u of x psi of x. Okay, so psi now depends on the location. What happens when we apply this transformation to the Dirac-Lagrangian? But I have to check, right? L Dirac is psi bar I gamma mu d mu minus m psi. What's the problem? That now we have a local transformation. So if it's local, that means when we take the derivative, it also change the, we end up this term. So L, we go to L prime. For the psi bar, this is just I E minus I Q chi, psi bar. Gamma mu. And now we have these two terms, which we have the derivative acting on. Right? So the E I Q chi d mu psi plus I Q d mu chi E I Q chi psi. And then the mass term is not affected because the mass is just a scalar. So minus m E minus I Q chi psi bar E I Q chi psi. So overall, this is the same Dirac-Lagrangian with this extra term that we have here, minus Q psi bar gamma mu d mu chi psi. What did I just show? What? No, right now the only thing that I showed is that if I take the free Dirac-Lagrangian and I apply a local gauge symmetry, the Lagrangian changes. So it's not invariant under local phase symmetry. That's supposed to be expected. Yes. Right? So free particle Dirac-Lagrangian is not invariant under local U1 local phase transformation. Not surprised. Yes.
לא ברור לי איך הנגזרת משתנה.
איזה נגזרת?
הדומיו. תחת הטרנספורמציה.
The transformation was psi equal to psi goes into psi prime, which is EIQ chi, which is a function of space and time in general, psi. This is a phase. It's a local phase.
אחרי זה שנעשה את הגייג' כאילו...
No, what I did, I just looked, okay, so let's put that in the Lagrangian. I put it in Lagrangian, and that's what I got. There is this extra term because now when I take the derivative, then it's not psi prime, so I have two terms which depend on mu. So one term is what I would expect to see if the Lagrangian was invariant, and there is an extra term. Okay.
So just to make clear, the derivative of chi with respect to mu is it's usually 0 unless mu is like x, right?
Well, it's usually 0. Mu is 0, 1, 2, 3.
Yeah. So if
Mu is 0, 1, 2, 3.
Yeah. So if mu is 0 or 2 or 3, the derivative should be.
I know x. Sorry, x. I mean, of course, globally, right?
Oh, okay.
3D. So it's not just one dimension. If you want to do one dimension down, that's okay. X is general space. It should be space and time. I'm allowing also the phase to change with time. This is completely general. So, if you want to make the Lagrangian invariant again, what do we do?
You need this must be
No. That means that this Lagrangian by itself, this Lagrangian is not invariant, right? But I can make it invariant. How do I make it invariant? I add a new term, right? So to make the Lagrangian, to regain symmetry, must add a term to the Lagrangian. Yes?
מאיפה באה ההנחה שהלגרנג'יאן צריך להיות אינווריאנטי תחת הטרנספורמציה הלוקלית?
I'm watching that one way. There is again. In physics, we try to find if there is some underlying hidden mechanism. It's an idea. It's Hermann Weyer's idea. It turned out to be working. Right? It turns out that all the interactions of the standard model, just erase that sentence, you can gain from the requirement of symmetry of the Lagrangian under local transformations. Why? I don't know. You can say, you can simply ask, okay, why is Newton's laws like that? We don't know. We're trying to find if there is something hidden below them, deeper. That takes you one step deeper. Why is that true? I don't know. If that's true, I don't know. Maybe tomorrow they'll find a new particle that does not obey that. As far as we know, Mother Nature is like that. Why? I don't know. Yes?
Does that change the topology of the space or something like that?
I'm not talking about the topology of space. I'm not changing the structure of space. This is not geometry. Okay? String theory does that, but I'm not expert in string theory. Okay? But you start to see the relation between that things. The old one. These are 20th century theories. Okay. So what do we need to do? Add a term to the Lagrangian, and we need to determine the transformation law of this new term, such as to cancel exactly this new term that we have. Must one add the term to Lagrangian to determine the transformation law of this new term.
If you add this term to the Lagrangian, all the Lagrange equation will change.
Wait, such that the Lagrangian stays invariant. For the question, yes, Euler-Lagrangian equation will change. Yeah, you have a new term, you have a new equation. Now the equation will describe also other things, such as interactions. Yeah. So how do we regain back the symmetry? We gain back the symmetry by replacing the term here, right? The partial derivative with respect to mu with what is known as a covariant derivative. So we replace. Did you see covariant derivative anywhere?
In geometry and
Different geometry.
Differential geometry. Yeah, I told you. This is
Yeah.
a geometrical interpretation. Yeah. So here's how it works. We replace the derivative d mu with what is known as covariant derivative. Which is noted with a capital D, d mu. So everywhere we see d mu will be a d mu, which is equal to d mu plus I q a mu. What is a mu? It's a new field. Do you know what field is that?
Photon.
It's photon.
Look like some sort of first order.
So in order to cancellation of the unwanted term, right? By determining the transformation of a mu by the unwanted term, if a mu will transform as a mu of x will go to a mu prime of x, which is a mu of x minus d mu chi of x. Let's make a direct substitution. So, check. I psi bar gamma mu b mu plus I q a mu psi. That will transform as I psi bar e minus I q chi gamma mu d mu plus I q a mu minus d mu chi e I q chi psi. Just made a transformation, but now using the covariant derivative instead of the regular derivative that we used earlier. So, this is, let's open it. This is I psi bar e minus I q chi gamma mu e I q chi. Then we have I q d mu chi psi plus d mu psi plus I q a mu minus d mu psi psi. Just plug everything in here. Which is I psi bar gamma mu d mu plus I q a mu psi. Which is what we want.
Wait, what is that?
I just transformed.
Okay.
I set up the transformation of A.
Cons
I just set up a transformation. I just replaced the derivative with a covariant derivative. I set the transformation law for A. And then I just look what happened when I write down the Lagrangian, the new Lagrangian, is this additional term.
And the master doesn't change.
The master doesn't change it. So if we just
why
prove
that true?
what?
That a mu x equal to eta mu x.
That's not equal to. This is I set the transformation law of A. It was my choice.
Okay, so it's a
I added up-
definition of
Yes, I added up a new field. What did I do? I did two things. I added up a new field, the A mu, to the Lagrangian. Two, I basically enforced or claimed that this new field A mu will transform locally under this transformation.
and you will show us white photon.
Right.
Okay.
Right now, I just did a mathematical manipulation on the Lagrangian because I want the Lagrangian to be invariant, and I got what I wanted, right? Because L Dirac now, psi bar I gamma mu, but now it will be a d mu minus m psi, which is equal to psi bar I gamma mu d mu minus m psi. That's what we had previously. And now we have a new term which is minus q psi bar gamma mu a mu.
How do you know
Psi.
it is valid transformation for field?
I don't understand the question. I define it now. So
Okay,
that under
define it.
local phase transformation,
How do you know
this is how A would transform.
A
I did not give it
is
yet a
something
physical.
that is-
I did not yet give it a physical interpretation. I just added up this field. I'm playing a mathematical game right now.
Why there is a field like that exists or something?
I said that if such a field exists,
Okay.
so far I'm not doing anything physical. I'm playing a mathematical game. I'm saying if I have such a field, if I take the Lagrangian, which I know is not invariant under local phase transformation, and I add to it this term by replacing the derivative with a covariant derivative, which means that I introduced a new field. And if this new field transforms in that way, then the new Lagrangian will be fully invariant under local phase
Okay.
transformation. This is a true statement. And in other words, what I did, I took the Dirac Lagrangian and added to it a new term, which looks like that.
Historically, what came before?
I said
and
that.
How do you use it?
So this what is this? This is a gauge invariant Lagrangian for spin-half Fermi. This is a gauge invariant Lagrangian or spin-half fermions under local U1 gauge transformation. Okay? So clear what I'm saying? So, the first term is for the free fermion. Right? And that term, if I remove the A mu, what did we get without A mu?
The
J.
The current, the conserved current, right? So this term here, right? This is equal to J mu A mu. Cool. So what is that?
without
Of course. What does it represent? What? This is an interaction between the spin half particle. EM. This is interaction. This is a Q here. This is the interaction between the fermion and photon. So, again, summarizing, right? The requirement that the physics is invariant. This was the starting point, right? We wanted the physics to be invariant under local gauge transformation, and we ended up that this requirement implies existence of what is known as a gauge field. This is a gauge field. Which couples to the Dirac particle, right? And it so happened that this coupling to the Dirac particle is exactly the same as the photons coupled to the Dirac particle. Surprise, surprise. This may be a coincidence. I don't know. Maybe. Maybe not. Maybe there's something very deep in here. Okay, you following? Right. So, in fact, that's the entire quantum electrodynamics. All QED can be derived from the requirement of invariance under local V1 gauge transformation. So, now what is left is to show, that was a question that one of you asked me, how do I know that A mu really represents a photon, this new field? Well, it has all the properties needed for the photon. So let me, it's okay, I can erase. See the magic, huh? Now I'm going to erase the board. What is left is to show that this A mu is really what we call a photon. Although so far in the derivative, nothing really tells us that this has to be a photon. But it is, of course. So physically, A mu x is appropriate to describe a photon. Questions for me? Yeah? No. I cannot be talking when I'm there. Quiet when I'm I don't know if you've seen it, right? That in electromagnetism, did you see that all electromagnetic interactions can be described when we're replacing P mu with P mu minus Q A mu? Did you see that in classical ENM? Yes. Yeah, who saw that?
What's each term represent?
What? This is a charge. This is a full momentum of a charged particle. This is classical ENM.
We didn't talk about four vectors.
Yeah. And this is the potential. This is the four potential. No.
Maybe
Scalar potential and the vector potential. You don't see that in the end? Okay, well it's there. Nobody showed it to you, but it's really there. And of course, when we take that and turn it into quantum operators, this will get into quantize. P will get into I d mu, and it will be I d mu minus Q A mu, or d mu gives d mu plus I Q A mu, which is just d mu.
What is that transformation from momentum to
What?
for momentum in what?
If you have a charged particle with form momentum p mu, and you want to describe an electromagnetic interaction, then you can write your equation by replacing p mu with p mu minus qa. That I thought you might have seen that, but if you didn't see that, that's okay. It is there. You did not put a lot about. Okay, I understand you didn't see it, but it's there. Trust me on it. Second, we spoke about the gauge transformation, right? A mu x goes to A mu x minus d mu cut x. Now this is the transformation of the Maxwell's equations. Okay, I don't know if you see that. Is the transformation of Maxwell's equations. Again, classical. Don't need the quantum mechanics. And the third is, of course, this interaction term. Interaction term.
What is high in the transformation Maxwell equation? Just
General. Just a general. So if you've seen that in classical E&M, then this will not be any surprise to you. So with that, we can now finally write the full QED Lagrangian. Right? L QED is psi bar I gamma mu d mu minus m psi minus j mu a mu. Then what is left? So that what is left? Is that the full QED Lagrangian? Minus 1/4 f mu nu f. Right? What is this term? Right, yeah, this is a free spin half particle. What is this term? Right, free photons basically.
Yes.
And this is the interaction between them. Cool, isn't it?
Yes.
Very cool. Right? And you nearly get it for free. Exactly free. So, free fermion, kinetic term of free fermion. This is interaction term. This is a kinetic term of free photon. Now, we sort of spoke about them, but we did not define them, so now is the time to actually properly define them. Any boson, photon is a boson, right? That is obtained by gauge symmetry of the Lagrangian is known as gauge boson. So when we speak about gauge bosons, that's what we really mean. We make a symmetry, and we ended up with new particle. Right? So any boson that is obtained by gauge symmetry of the Lagrangian is known as gauge boson. Okay, so one comment. What if we have a massive photon? So comment. Can the photon have mass?
No.
No, why not?
Travels in the speed of light.
What?
It travels in the speed of light.
No, but I'm not talking now about traveling at the speed of light.
Yeah.
Within this theory, what happens if the photon would have a mass? If the photon would have a mass, right?
It doesn't show up in a kinetic term?
Right. Then you have to add a mass term of the photon to Lagrangian. Then the Lagrangian would have a mass term of the photon, which would look something like 1/2 m photon squared a mu. And then it will transform under gauge transformation or local transformation to 1/2 m gamma squared a mu minus d mu chi. Mu minus d mu chi, which is obviously not the same as 1/2 m gamma squared a mu. So what does it mean? What? Right. So if we insist on this gauge invariance as a guiding of making interactions, that means that within the framework of the standard model, the photon cannot have mass. Right? Within
Maybe
standard
AMU
model.
just not the photon.
What?
I will say maybe AMU just not the photon, the photon can.
It will not be a photon. You're right. Within the standard model, the photon cannot have mass. Yeah, if you accept this idea of gauge principle, then you can say, I don't believe it. This is a nice idea, maybe mathematically it's very nice, but this has nothing to do with physics, right? Maybe, we don't know. But, as long as you accept this idea that everything is derived from the gauge principle, then you will not have a mass for the photon. So, yes.
למה אם לפוטון היה מסה, אז זה היה הביטוי שנתחיל?
למה זה היה... אני חושב שהראינו את זה, זה הפרוק האיקוויישן.
שמה?
פרוק הלגרנג'י.
לא דיברנו על אנרגיה, כאילו...
So energy. The Lagrangian. This is the master of the Lagrangian. So that means that what? So the QED mediators would be photons, right? And they are massless. What else do we have? We have two more interactions. Right, so we have the strong, and what about the strong interaction? What are the gauge bosons of the strong interaction? Do they have mass? No, they don't have mass. From the same reason. What about the weak interactions? Yeah, they do have mass, right? These are what are the gauge bosons of the weak interaction? So how we solve that? What? No. How do we solve that?
We have another Lagrangian or another.
No. Okay, that's the Higgs. That's what we're going to see next week.
Ah.
Right? So weak interaction has, we have to come up with a different idea, and that's the Higgs. But let's stick with that.
Wait, but we have another hour, so will we see it today?
See that you're optimistic, but we're not going to see it. Okay. Gee, it's already 5. We don't really have time. Okay, just as a final remark, right? So this is LQED. I wrote it that. Really, what I should write is sum over all the fermion types. Right? And fermion as well, right? And the Q
Of all F in the system, right?
of all F in the system, right? These are all the fermions. So basically, everything for all the fermions is the same. Of course, the charges are going to be different, right? For the electron to be a -1, for the up quarks it's going to be 1/3, for down quark opposite, right? Up quark would be 2/3, down quark would be a -1/3, etc. Right? But generally, this term does appear as such in the standard form. Okay, questions? No, really not. So I'm going to skip now the weak interaction. I tell you, basically I'm skipping a whole part of the weak interaction because I had to cut some things. I maybe, if we have time later on, I'll say some words about the weak interactions down the line today. Let's speak about the strong interactions. That's good, read it, really. Yeah, very cool. QCD. So in QED we had a local U1 local gauge symmetry. In QCD we can do the same, but it's not going to be a U1. Why not? Because we have no color, right? We have colors, right? The strong particles do have color. And that comes in triplets. So we have 3s. So that means that we cannot use the U1, we'll have to use a little bit more complicated SU3, right? Special unitary 3. So we're going to have
Why the fact we have color means that
what?
we can
Yeah, wait, we're going to see that in a second. So in QCD, since particle carry strong interactions have color charge RGB, right? The underlying symmetry is what's called SU3, local phase transformation. Now, SU3 means a group of 3 by 3 unitary matrices A unitary matrix means that U, regular U, is equal to 1. That has a determinant of 1. Could actually be -1 as well. Just easier. Now, another thing about this group is that it's non-abelian. What does it mean, non-abelian? They do not commute. Yeah, the matrices do not commute. This is a non-abelian group, meaning the matrices do not commute. Yes, question?
All of them can can be written as cosine and sine of something, right? No?
Now it's a 3 by 3 matrix, it's not a 2 by 2, yes.
יש משמעות פיזיקלית לזה שזה קבוצה לא אבלית? שזה קבוצה לא אבלית?
כן, אבל לא יודע מה. I'll have to think a little bit and maybe the answer will come later. Yes?
The same symmetry shows up when you look at like the function of the eye. Is that the reason it's RGB? Because it's similar to the function of colors in the eye and reasons like that?
In the 1960s, where people looked at that, why did they decide to call it RG and B? I've got no idea. Rumor says it might be have to do something with LSDs. I don't know. Yeah.
But the creator of the groups are the rotation
Generator, yeah.
the generator. Yeah, just
One step at a time.
so
We're gonna
it
see it
can
at
be
the top.
written as
No, it's not Abelian.
I'm not.
What are you talking about? Okay, let's go on. Let's go on. Let's see. The matrices, generally we say the generators. Now, just to make sure where we're standing. Do you know what is a generator group? Who does not know? Raise your hand. Who does know? Raise your hand. Some people did not raise any hand. Refuse to admit. You refuse to admit. Okay, this is a basic in group theory, basically about generators. Let's see where we get stuck. When you get stuck, just raise your hand and then where we are. Right, now again, there is something very deep here, right? Because I'm claiming that essentially it has the same structure as QED. So basically I'm saying that this gauge symmetry is responsible for all the interactions we have in nature. That's a very, very strong and deep statement. Okay? Despite all the huge number of different particles, different interactions, everything that we're seeing in nature.
What about the weak interaction?
Like I said, weak interaction will have the Higgs mechanism.
What about the gravitation having?
That is not part of the standard model. So you have to. This is not the standard model. Talk about the standard model. So in QED, all particles had only one charge, right? Q, or multiplication of Q, right? Here we have 3 charges. Color charges. So in QED, the QED charge was Q, and QCD charges is R, G, and B. So we have 3.
What about like anti-R?
That's okay. That I can get to them by a minus.
Yeah. Because we are in groups.
That's okay. Let's look at the 3-particle Dirac-Lagrangian for quark. So 3-particle Dirac-Lagrangian for quark. One of the quark flavors, right? So rather than psi bar I gamma mu d mu minus n psi, now it's going to be sum over all colors psi bar color I gamma mu d mu minus m psi color. I did not put the color on the mass because from what we know, the mass does not depend on the color. It's the same mass for all the colors. Now, for the simpler notation, notation, we're simply going to write psi as a triplet or multiplet. Psi R, psi green, and psi blue. Similarly, psi bar is psi bar R, psi bar green, and psi bar blue.
12 elements.
What?
12 elements.
What? What do you say?
12 elements.
Why 12? 9, 3 by 3. How do you get to 12? Let's talk about, I have 3, right? R, green, and blue. So 3 by 3, I have 9 total. Come on. Each one of them is Dirac's minor. Add up another level. It's not a 12. This would be a 4 complex if you want, so it would be an 8. Yeah, that's fine. But I don't care about the internal degrees because they will tell me about the spin, etc. I'm not talking about their interactions. That's what I care about. I have to look at the Dirac Lagrangian and to see how to derive the interactions of these particles. Right. Now look at this SU3 symmetry group. So, any 3 by 3 matrix in general, right, I can write as a combination of 9 complex numbers. What is Uij? Some complex number. Right, Uij, some complex number. No, it's okay. Now, because it's unitary, right?
The determinant is one.
What does it mean?
The columns are
U dagger U. How many constraints does it put? Unitarity? Right? So, how many degrees of freedom does that take? 9, right? So, how many were left?
9.
So, we totally have left with 9 degrees of freedom. So totally 18 degrees of freedom.
Wait, there is 9 degrees of freedom. 18. 1 for the real part, 9 for the real part.
Oh, okay. Right. So that means that we can express U of 9 linearly independent 3 by 3 matrices. So U can be expressed in terms of 9 independent 3 by 3 matrices. Now, one of these matrices is going to be simply the identity matrix, which we multiply by any complex space that we want, we don't care. So one is the identity. Right. It's identity, that means that it's not relevant for the transformation between the different colors. Essentially, what is transformation between different colors? Not sure that you're
Rotating.
Physically, what does that represent? What did we do in QED? We had the Dirac-Lagrangian. We multiplied by a local phase, which was a U, which was a one by one matrix, basically, right? And we demanded that the Dirac-Lagrangian will remain invariant. That was and then we ended up with interaction, right? Interaction with another field, which we call the photon. Right. So what does this matrices represent? Interactions, right? That will be interactions. Interactions with what? Gluons. How many gluons there are? 8. Right? One is the identity matrix, so it is a particle interacts with itself, so I don't need anything. And then there will be 8 gluons. Right? Now you see these gluons, what do they carry? They carry color. So they can connect particles with different colors. Yeah, you're all with me? Not that sure about it. Yes.
זה אומר שהגלואנים עושים
כי הם מקשרים. The gluons connect between, I'm going to write down the Lagrangian in a second, right? And the gluons will connect between different terms inside the Lagrangian, right? Now, the difference was that before I had psi, it has the internal degrees of freedom, but there was no color or anything. Now I wrote psi as it's a multiplet, right? And psi bar was a psi r, psi green, psi blue. So there was a term that connects them, and that I can start from psi r and end up with a green psi. That term would be by interaction. That interaction is the gluon. That's exactly what I'm describing here. Yeah.
By express in terms of 9 independent matrices, we mean span of matrices or multiplication of matrices?
Span, not multiplying.
Oh, no.
Again, I'm going to put out the generators here of the group, right? This will be the generators. These are the local phases. I'm allowing my wave function here, right, to undergo a local phase transition, and the Lagrangian will remain the same. That's the whole point that I'm doing here.
But the sum of two unitary matrices does not.
Wait, everything will be clear.
Does not have to be unitary.
What? It don't have to be? Guys, there's too much noise.
Unitary.
No, everything is unitary.
I plus I is 2I, and that's
Everything is unitary. So one we said is the identity matrix multiplied by some complex space, which I don't care. Right? 8. These are from the SU3 group. Can be expressed from the SU3 group. Can be expressed in terms of 8 independent emission generators, which we call TA. TA or TL? Yeah, TA. So a general SU3 transformation, SU3 transformation is written as U general is E I. Now I have a GS, that's what replaces the Q, that's a coupling constant of the strong interaction, right? And then TA psi A.
An A running from 1 to 8 or 0.
A runs from 1 to 8, yes. Now, a generator, for those of you who don't know, right, infinitesimal transformation, such that when we apply them as many times, we can express all the, basically like the basis, right? We can express all the possible transformations that there are. Or all the group elements, sorry. So, this is GS, this is the physics, right? This is the QCD coupling constant. Psi, what are the psi A? No. This tells you how much you are rotating in each direction. Right? So these are 8 parameters. Parameters that define how much. So the nice point. The specific rotation that define the specific rotation in SU3 space. Some TA. These are the 3 by 3 Hermitian matrices. Now the TAs, of course, there's more than one way of writing them, but there is a standard way which is based on Murray-Gell-Mann. So these are called the 8 Gell-Mann matrices. So Gell-Mann matrices TA lambda A over 2 and the lambdas, I just put it because it's just nice. So the lambda 1 0 1 0 1 0 0 0 0 0 lambda 2 is 0 minus I 0, everything else is 0. Lambda 3 is 1 0 0 minus 1, everything else is 0. Lambda 4 is 0 0 1 0 1, everything else is 0. Lambda 5 is 0 0 minus I 0 0 0 I 0 0. Lambda 6 is 0 0 0 0 0 1 0 1 0. Lambda 7 is 0 0 0 0 0 minus I 0 I 0. And lambda 8, 1 over square root of 3, 1 0 0 0 1 0 0 0 2. Minus 2. And the 3 colors will be represented in these spaces when we're using Gell-Mann matrices. The 3 colors will be represented by 3 vectors. So R, this is going to be 1 0 0. G is 0 1 0, and B is 0 0 1. You all with me?
How do you represent Next question. How do you represent an anti-quark with red color, like anti-red?
Anti-red. Should be a minus here. Give you the anti-red. Actually, I'm not 100% sure. I'll check it out. Again, difference between QED and QCD. Right? The concept is the same concept. We want invariant under local phase transformation. Only here, because we have three colors, the local means that the generator is not just the one matrix as we had before, but 8 3x3 emission matrices. TA. TA, there are more than, of course, there's more than a single way of representing them. The one that is commonly used is by Murray-Gell-Mann. These are the Gell-Mann matrices, TAs. Right. In the spaces, the R, G, and B would be zeros. I think it's a minus. I'm not 100% sure, so I don't want to tell you something I'm not sure.
That is just one representation, right?
Yes, but this is a standard.
So there's not another useful representation.
Fine use.
Something common in papers or something.
What?
Something common in textbook or
No, textbooks you only find. Okay. I never saw anything in textbooks that. I think in some textbooks you can find other representations, but there will also be. This will always be there, and could be some others. Guys, questions? Comments? Concerns? Yes?
עכשיו 5:30 יש משהו להפסקה.
Okay, let's finish that and then well. So, what do you have? Where are we? So we say that similar to QED, the Lagrangian should be invariant under local phase transition, right? So psi, U psi, L should be invariant. Let's see, psi bar I gamma mu d mu minus f psi goes to psi bar u dagger I gamma mu d mu minus m u psi. Now, the Gell-Mann matrices are constant matrices, which means that everything here commutes with them, and so the Lagrangian is invariant. Right? So this, so U is constant matrices. Right.
Why does it commute with gamma matrices?
This is globally. Okay. So globally, for globally, then the U's are just constant. So no problem, right?
Why the fact that they are constant means that they commute with gamma matrices?
Because they don't live in the same space. You operate on psi. Okay, and you dagger on psi bar. Okay, it's not the same. Okay, this is confusing a little bit, right? Gamma commutes with the internal parts of psi. This is a color, so this is a different world. I don't know, space. U's are constant. So what about, so globally you're constant, that's not a problem. So we have a global SU3 symmetry, which that means global SU3 symmetry, which in identical way to what we did with QED, that means conservation of charge or color in that case. Of color charge. Exactly what we did, so there's no point in doing it again. Yes.
איפה בא לידי ביטוי העובדה שהדטרמיננט היא 1?
פה אני לא חושב שהיא באה... שיהיו י' דגר זה 1. י' דגר זה 1. If the determinant was not 1, when I cross u around here, I will not get a 1. Okay. What about local? So now we require that the Lagrangian be invariant under local symmetry. So require invariance under local symmetry. Which is psi a of x. That's a bit more tricky, but we repeat the same thing we did with QED, right? So the first thing we do is replace the derivative with a covariant derivative. So d mu will go to d mu, which is d mu plus I gs, that's the coupling constant, ta g a u. What are the g mu a? Ga mu of x. What are these? These are the glue ones. This will be 8 new fields. 8 new vector fields. Each of them corresponds to one of the 8 generators. One of the SU3 generators. Right, so we just ended up discovering there should be 8 new ones. Now in QED, we had the transformation law of the A, of the vector field that was introduced, right? We had A mu of x was transformed as A mu of x minus B mu of x, in order to cancel the additional term that we got in the Lagrangian. Here we got the more complexity, and that is because the symmetry group is
bigger.
non-abelian. They do not commute, so we have to compensate for that. Okay, but here the symmetry QCD, of course there should be 8 of these, right? Because we have.
So we need to add another.
We need to add an extra term, right? Because QCD, the symmetry group is non-abelian, which means that the matrices do not commute. So the transformation is not going to work. So if we try, just a second. If we try to repeat the same thing we did with the QED, so writing something like I gamma mu d mu plus I gs g mu a ta psi minus m psi equal to 0, that's not going to work. מה שכחתי? מה?
ב-Q is H, לא אמור להיות A מיו X מינוס גם מיו סיין?
כן, יש לו סיין. תודה. So we need to add a term. So must add a term. That cancels the commutator. So that means that the transformation law of the new field G mu A should be G mu A goes to G mu A minus T chi D D mu chi A minus GS F A B C chi B G mu C. F A B C, they have a name which you may have heard of. These are called the structure constants. Of the SU3 group. And they're really defined by the commutation relations. Between the generators of the group, TA, TB, is I, F, A, B, C, DC. Of course, what was the term if this was an abelian group? Zero, right? Abelian group means that all the matrices commute, so this would simply be a zero. If it is not, then these are not zero.
A, B, and C are numbers.
Are numbers, yeah. Now,
1 to 8.
Yes.
Okay.
So the third term appears because SU3 is not abelian?
Yes.
אסף,
Yes.
לא ברור לי איך מקודם בלוח שהמחקת, עשית, כאילו, הפעלת את הטרנספורמציה, היה לך בצד שמאל U דגר, בצד ימין U. למה הם לא מבטלים אחד השני? כאילו... אוקיי, אז מאיפה בא לך...
If it's a global.
מה ההבדל בין גלובל ללוקל?
Again. A global phase, right, is that we wrote down U, right? Should I write it? It's EIGSTA chi A, right?
Okay.
If, now again, GS is equivalent of Q. This is the coupling constant of the strong force. TA are the generators, right? For those of you who don't know, right? Again, the rotation group, right? We can make a rotation, but there are three principal axes, right? So the rotation, so the generators will tell us which are the axes, and the chi tells us how much we are rotating, right? So we can rotate around this axis in a little bit or in a big bit. Okay, so this is the difference around this axis. So this is a different t. A little bit is the chi. It tells us how much. Okay, so this spans the entire space of SU3. Now, difference between local and global. Global means it's the same chi, the same rotation everywhere in space. Local means that it is different in different locations in space and can be in different times in space.
Okay.
That's the difference. If it's local, if it's global, when I wrote the Lagrangian, there was this derivative. I don't care, right? It's a zero derivative. Then I get the u, regular u, which is I can move the u.
Okay.
If it's local, I have this extra term.
Okay.
Repeat what we just said in the first half of this lecture. That's all. Now, because the g's are not abelian, right, the transformation law of the g's would give us an extra factor with this f, which f is the structure constants of this SU3 group, which is defined by the commutation relations, the generators of the group, right? Now, just for completeness, I can write down these terms. The only non-zero terms would be f. I just write it to you, but you can find it in any textbook. F123 is 1. F147 is F246 is F257 is F345 is F516 is F637 is 1/2. F458 is F678 is square root of 3 divided by 2. And the cyclic permutations are the same. Anything else is 0. Now they have a few mathematical properties which you can imagine, and you will work this out in your own. Now, so similar to the, nothing fancy here, just to see where everything comes from, right? Everything. What are you happy about? Give you extra homework. So you have this.
זה מזכיר לי את החישובים של להרים אנטנזון. אוי.
Have to do it once in your life.
וזה מעלה חיוך על הפרצוף שלך?
Okay. Right. So, the same as we did with the QED, right? We must add to the Lagrangian an interaction term, which we already got it, plus a term that would look like L2L, a term that would look like minus 1/4 G mu A G mu A, which is the QCD equivalent to the F mu nu F mu nu, right? But because we have this extra term there, so for the Lagrangian to be invariant, but for L to be invariant, definition of G mu nu A is different than the QED equivalent, which is G mu A is d mu G mu A minus d mu G mu A, and now we have the addition minus GS F A B C G mu B G mu C. And that means that this addition means that we do have term, so we have terms such as GS squared F A B C F A B prime C prime G mu B G mu C G B prime mu G C prime mu. What does this term represent?
The second order.
What does this term represent physically? Interaction between what? Two gluons. Right, so two gluons can interact with each other. Right, so we'll have something like gluon and the gluon come and two gluons go. What? That's what's written here.
You told us the
two gluons.
binary diagrams you only have like two. You can't have a
You just
vertices.
look
Yeah,
at
but
the
for the
first order.
gluons you can have that.
Oh, so fun.
If you have only gluons in the system or something like that.
That is likely what is caused the gluons to be only short term. Right? And you also have terms like
But interaction like that has small probability to occur, right?
no.
No.
It depends on what is GS. If GS is much smaller than 1, then yes. If GS is approximately 1, then remember we spoke about the coupling constant of the strong force is of the same order as unity, then no.
Okay.
Right. And also some terms of the form GS, F, A, B prime, C prime, D, mu, G, mu A, G mu B prime, G mu C prime. What is that? Should be easy, right? There's three ones. So the requirement for invariance, local symmetry under local gauge theory gives rise to gluon interaction. As opposed to photons, which as we know do not interact with each other, gluons do.
Three interaction simultaneously? No. Oh, I'm not understanding.
This term represents interaction of two gluons. One gluon again.
Oh.
That's not bigger.
So one
yeah, so wait, just so let me bottom line is in non-abelian gauge theory there are interactions of gauge bosons not only with fermions but also among themselves.
So gluons have color?
Yes. So gauge bosons. That's exactly what it means. The gluon must carry color. Gauge bosons are also charged. Under interactions. This is exactly what caused the colors to be confined. Yes.
איך אתה רואה כאילו מהביטוי שקיבלת שזו האינטראקציה?
I have a G mu nu, G mu nu. Okay, I have this term. This would represent the free gluons, right? The same way as we had with the photon analog. We had the F mu nu, F mu nu. So here we have a G mu nu, G mu nu, right? But because of this non-abelian, say, property of the group, we define G mu nu. We cannot simply use the same definition as we had for the photons, but there is this extra term, which is there because of the non-abelian property. Okay. And so when we write down the interaction term, we always have this term interacting with one of these terms or with itself. So new terms basically appear when we open up. That's all. And this new term essentially gives rise to self-interactions. There's a very delicate game here between the math and the physics, right? This is a mathematical game, right? We started with a mathematical requirement of invariance under local gauge symmetry. We said, let's see where this is heading, right? And we ended up that we must have this type of terms, right? And then we say, look, this mathematical idea turns out to be right. It describes very nicely what we see in nature.
אז כאילו, שתי הביטויים הראשונים, דו, מיו, ג'י, שני הביטויים האלו הראשונים מתארים גלואון חופשי.
לכאורה, כן.
והביטוי האחרון מתאר אינטראקציות של גלואון עם גלואון אחר.
לא, no. The interaction of the gluon with other gluon would be this one, will be this one, basically. Right? So we have a G mu nu, G mu nu. So you have to have this, the G mu nu, you have to open it and write it with another. Right? So you just copy that with the lower indices. And then you'll get terms that will look like that times the other term, which will give you that. Or that times one of these terms, which will give you what's written here.
הביטוי הראשון שתקבל שזה כאילו כאילו הביטוי הראשון שמשני הסוגריים זה והביטוי הראשון שם זה יהיה, מה זה יעשה?
This will be identical to what you see from the photos.
שזה גלואון חופשי, לא?
In principle, yes.
Okay.
But they will also be these terms. You cannot avoid them.
Okay.
Okay? This is the conceptual difference between QCD and QED. And look, the beauty here, I'm using exactly the same mathematical structure. I have the same mathematical demand. I do the same thing mathematically. I just make sure that I'm fully consistent mathematically. And voila, I got something which actually describes the physics as we see it. So there must be something deeply right in this mathematical interpretation of symmetry. We know it's incomplete, but we know it's right because it describes what we see. At the end of the day, remember what I told you in the first lecture. Physics is an experimentally driven science. You make an experiment, you see some result. And a theory is good as long as it reproduces the result. If it does not, it may be a beautiful theory but irrelevant. If it does, then there is something right in it. That's what we have here.
Okay.
That's all. Okay? Right. So, the full QCD Lagrangian, now we can write it down. QCD Lagrangian. Again, you will see it as part of the standard model Lagrangian. LQCD. There's some overall quarks because only they carry the strong force. Psi bar quark, I gamma mu d mu minus m quark, psi quark minus 1/4 g mu nu a, g mu nu a. With all the definition, and the sum is of course over 6 flavors. Now, similar to what we did with, so this is the QCD Lagrangian. Now, similar to QED, of course, we have a vertex that contains the quarks and the gluons. Right? This is very similar to what we had previously. So, interaction between fermions and gluons. Interaction between quarks, fermions, and gluons. Right? We have this term that comes from the covariant derivative in there, right? It's I psi bar gamma mu I gs Ca Ga nu psi. which is minus GSTA psi r gamma mu psi G mu A, which is what we had previously, minus J mu A G A. That's exactly the quark, quark, anti-quark.
אתה יכול להסביר, כאילו, לא ברור לי מה זו המשוואה הזאת.
This is a term, again, remember what we had. I'm just repeating the same thing we did with the QED. Right? Remember what we did. We started from a free particle Lagrangian. Then we said we want to change something to make it invariant under local phase transformation. So we changed the derivative to a covariant derivative, d mu. We added up a term in the derivative. Then we said this term at the end give us what? Interaction between the QED fermion, spin half fermion, and the photon. QCD, we do the same, and we get the same. We get this extra term. This is the extra term that we get when we replace the derivative with the covariant derivative. And that really gives us a coupling between the quarks, represented here by the currents, and the gluons. That's all. It's exactly the same thing. The difference is because it's a nanobillion. We had 8 gluons. We have colors. We have 8 gluons, and we have gluon-gluon interactions. Because to compensate for this nanobillion mathematical
sounds pretty chaotic.
It doesn't sound chaotic to me. To me, it sounds like a miracle, right? You start from one. You start from, in a sense, right? You start from a mathematical assumption which you don't really have a good physical understanding, or at least a good physical motivation to have. And then you write it down and you just follow the math, and the math gives you exactly the interactions that you're seeing in nature. So that means that there was something, some very important and correct insight in this initial mathematical demand. And the initial mathematical demand was for a local symmetry. Local phase symmetry. That was local phase local invariance under phase invariance under local phase transformation. That was the demand. That was the mathematical demand, and somehow you get back what you're seeing in nature. So there's something must be something very right in that initial assumption. Yes.
What is the meaning of raising or lowering the A index?
What do you mean raising or lowering? Well, I keep, since I'm summing over A, right? A represents the 8 matrices that we have there, right? Basically the 8 generators, 8 couplings between the different colors. So there's always be one upper and one lower. I'm just using Einstein's summation convention, that's all.
Can we see from this Lagrangian that why in the nature we only have, everything is white? Like the proton have all 3 colors together, and mesons have only quarks and antiquarks, so
from that by itself, I don't think you'll see. Maybe there's something that I'm missing here.
where we see it in the course.
There is a summation over A here, but do we see it? No, I don't know if you can see
Is
it.
there a theoretical explanation?
I have to think of that and come. I don't remember right hand.
כאילו, צד שמאל מתאר לנו שיש אינטראקציה בין שתי קווארקים, וצד, כאילו, צד ימין שאתה מפתח, אתה מבין שכאילו צריך להיות פה זרם של, סוג של זרם של גלואנים, שזה יוצא?
כן. Look, again, remember, you can look at it in a different way, right? You can think of a quark, single quark, that emits a gluon, interacts with a gluon. This is a vertex, right? This represents a vertex. You have a flow of quark and a gluon. That's what the vertex looks like. Okay. I wish there was an exam, and I'll make sure that you actually understand it properly. If there is no exam, review, because this is exactly what we discussed a few weeks ago when we discussed this Feynman diagrams and Feynman rules. Go back to the Feynman rules. Now you'll see that it's exactly the Feynman rules that we're talking about.
זה אותו, זה כאילו, אותו נקודה שראינו עם הפוטונים, שכאילו, שיש זרם של אלקטרונים, ואז...
Yeah, it's identical. Okay, any further questions? Okay, so wow. So let's do, so the next is going to be somewhat easier. Slight repetition. If there is some repetition, I'll just skip it because due to lack of time. Repetition of some things we said, but in a slightly different way. Let's go over it quickly. There's a small punchline, not a huge one, but mainly to show you a few things. So the approximate QCD symmetry is, of course, the isospin. Approximate QCD symmetry is the isospin. Isospin is isotopic spin, right? So it's spin of isotopes. We already had one lecture about isospin. I said that it has basically, it looks exactly the same like spins, although it has nothing to do with the spin, because mathematically it looks the same. In QCD we have 6 quarks, right? So we have 6 flavors. Of course, each one has a different mass, but the mass of the up, down, and down quark are very, very similar, right? Mass of the up is 2.3 MeV. Mass of the down is 4.8 MeV. Of course, we don't see them, because what we do see is the hadrons, and the hadrons that we do see, that is, we don't see. And the mass of the hadrons would be pions, because the lightest would be about 140 MeV. Mass of the protons, nearly GeV, and the same for the neutron. So we can take the limits of one m down is approximately the same as m up, and there is no 1 and 2, no electromagnetic interactions. And we end up with full symmetry between protons and neutrons.
But it's not really the case.
Well, it's approximate symmetry.
Okay. Right.
But it is true that the difference, right, m down minus m up is much smaller than m hadron. Anything else that we have here, right? And also that we said no electromagnetic interaction. So again, alpha, right, is 1/137 is much more than alpha strong, which is about 1. So it's not such a bad approximation. It's an approximation, but it's not a bad one. So this is an approximate symmetry. Which means that all the predictions we're going to get from here are approximately true. But, you know, right? I mean, for example, right, we'd say the masses of the protons and the neutrons should be the same. This is approximately true. Historically, of course, it started the other way around. People noticed that the proton and neutron have the same masses, and they started to think whether there is some hidden symmetry in here. Okay, so we already wrote the QCD Lagrangian, so let's write the QCD Lagrangian and use it to find the symmetry group. So the Lagrangian, QCD Lagrangian of, let's just look at the up and down of two quarks. So we have L is psi bar up I gamma mu d mu minus m up psi up plus psi bar down I gamma mu d mu minus m down psi down. Remember that this psi up and psi down, they really are vectors of 3, right? For the 3 different colors, right? So the 3 different colors that we have. We can write it in a compact form as psi bar up, psi bar down, I gamma mu d mu 1 0 0 1 minus m up 0 0 m down psi up, psi down. So this and this is the same, just written in a slightly more compact form. Or even a more compact form, we can simply write it down as psi bar I gamma mu d mu minus m psi, where psi is psi up, psi down. And psi bar is psi up bar, psi down bar. And the mass is of course the matrix m up 0 0 m down. So far I did not do anything, right? I just rewrote the Lagrangian in a more compact form. Now let's apply a global transformation. Right. So it's a global, so psi goes to u psi, which is E I alpha. I wrote this a tau. Psi. Tau is sigma 1/2 sigma. These are the generators of the SU2. Right. SU2 group in the 2D representation. What does it mean, SU2 group in the 2D representation? What did I just say? Rotating between what?
This one is up and down.
Up and down, right? I wrote it here, and then I said, okay, I have a phase which can rotate between up and down. This equation. Yeah? What are the sigmas? That's Pauli matrices, right? And what is the alphas?
From the other equation.
No. No. What is the alphas?
Fermi.
It says how much we're rotating, right? So parameters describing how much we're rotating, right? Pauli matrices. So put this inside the Lagrangian, and we get that L goes to psi bar u bigger I gamma mu d mu u psi minus psi bar u bigger m u psi.
What we want to get? How do we want to get?
Wait, we look at the symmetry. That's an approximate symmetry, just to give you the idea of how to make use of this Lagrangian term. right? So
tau זה חצי סיגמה?
tau is half sigma. Yes. It's the standard notation. Now the first term we got no problem, right? These are unitary matrices. V mu here. Everything is unitary, so these terms cancel. What about this term? If we had m up equal to m down, then they will cancel as well. But if m up is not the same as m down, then this will only be approximately symmetry.
Yeah.
Right?
Here it cancels.
Yes.
Why?
Because I can switch u with m.
Okay, yeah.
Right? Here I can switch u here because it's just a constant. And
And
here I cannot do it because I have to have this. If I can, if it's the same mass. If they're not, I cannot do it.
why again? With what
Think
it
of
not
it for a second.
commutative?
This is a constant matrix. So, we said that mathematically, SU2 right, is similar to spin. Which means that again, this is already solid in a 2D representation, so we can write u as a half-half and b as a half minus. And these will be the I and I3 quantum numbers. That's we already said, so I'll just skip that. For the anti-quarks, we have anti-d is a minus half-half, and anti-u is a half minus half. Then, okay, pions, I think we already mentioned that, so I'm not going to write it down. Alright, let's just write it down for completeness. Write down for the pions. Pion class is up, anti-down. That's a minus 1, 1. Pion 0 is 1 over square root of 2 up, anti-up, minus down, anti-down. So this is a 1, 0, and pi minus is anti-up, down, which is a 1, minus 1. Okay. Yeah.
שתי שאלות. אחת, למה טאו מוגדר להיות ככה? כאילו, או שהוא מוגדר...
Convention, it's just a convention.
סבבה. שאלה שנייה, למה SU2 is similar to spin? כאילו.
That's how you define the spin. This is a symmetry group for which you have a spin.
Related to spin?
No, identical. This is the mathematical structure of the spin.
בגלל שכאילו, היצרים של זה הפעולים הזה?
כן.
סבבה.
דרך להסתכל על זה. Again, we can say the same for the raw particles that will decay into the pions, etc. Yeah, okay. Yeah, so just historical notes, and that I think is a really good time to finish. So the pions form a triplet, really. Same would be the rows. And historical, it seems that it turns out that people discovered that many hadrons, like the pions and the row, can be put in this SU3 symmetry group.
Plus SU.
Right? The same SU3 that we had for quarks, but not for the quarks. This was just for several hadrons. You know who are the guys who did it? Who are the guys who did it? So it was Yuval Ne'eman, Israeli, might have heard the name, and Maury Gell-Mann. Who? Maury Gell-Mann, independently. And so in fact, this historically, this was before the quark model. And the symmetry group was the same symmetry group that we just described, the SU3 for the quark model. Okay? And that's it. And I think this is a good place to stop. Right? Well, the quark model, by the way, when it was written, it was before the several quarks were discovered. They only knew about 3 quarks at that time.
What was the year that
This was 1961.
1961.
Yep.
We're getting closer.
Take your time. All right. Any further questions? I'll post the next homework, I hope today, this evening, if not then tomorrow morning. So we'll meet again next week, and then next week we'll discuss the Higgs. I hope we'll finish next week.
We will not discuss nuclear physics.
No, we'll not discuss nuclear physics, and we'll not discuss many other things. We won't discuss much in the in-depth weak interactions, which are very important. But that's how it works. This is a short semester.
יהיו עוד 2 תרגילי בית או 1?
לא יודע.
כן, שנראה.
בדיוק. There will be one today. Yeah. But,
כאילו, איך זה עשינו? זהו, עשינו את זה
לא, זה פשוט להראות שאתה השתמש באותה תחומת סימטרית. זה היה אולי צריך לחזור למרות אותו מבנה מתמטי שיש תסתכל על זה בתור שני מצבים